Bismillahirrahmanirrahim. Once the boundary conditions have been applied on our FE equations, the next step is to solve the equations to get the displacement components. Now, the most popular method for this, and which you must be already familiar with, is the Gaussian elimination. Now, it consists of two steps: forward elimination, and that is followed by backward substitution. Now this is step 1, this is step 2. Most probably you are already familiar with this, but just for the sake of completion, I'm just going to spend a few minutes on this one to list the steps taken for in this method. Now it can be another variant of this is backward elimination followed by forward substitution. Now in this case, this becomes step 1, this becomes step 2. These are actually identical as far as the process goes, and either one can be done. We'll focus on this one today. Now the process will be demonstrated using a 4x4 matrix, and the stiffness matrix is banded, it is square, it is symmetric, and we'll just try to capture all these properties here. And it doesn't matter if it's a small matrix, because we are only going to demonstrate the steps. The same steps will be taken in for real systems on an n into n size matrix. Now this is the matrix on which we are supposed to apply this Gaussian approach. The force vector is this one. Now a word of caution here, although it is symmetric, it is banded, the zero here, and if it was a bigger system there will be more zeros. Symmetry because Aij is equal to Aji, and you have this matrix here, small matrix. But if it's a bigger system, usually you have this type of a situation where square matrix is there, but because it's banded, some zeros are here, and because this part is symmetric, just like we have the symmetric part, how it is stored actually, these are the non-zero numbers that your algorithm actually stores. Now you have this type of a system stored not like this in a full matrix form, but like this. This diagonal becomes this, the second principal diagonal becomes this, the second diagonal becomes this, the third diagonal becomes this, and so on. And then this becomes smaller and smaller, and then you have zeros here, and you have zeros here. So this results in a much smaller requirement for space. Now we are not going to demonstrate our algorithm on this one, this algorithm. We are going to demonstrate on a full matrix. If this is to be used, then there is a variant of the same approach, forward elimination and backward substitution, but that caters for this banded nature as well as the symmetric nature. We are not going to demonstrate it here. More advanced algorithms cater for that. But essentially the thinking is the same. So now our goal is to invert this matrix. Invert in inverted commas. We don't invert it. We want to find the values of u1, u2, u3, u4. We always do it by a process that is less computationally expensive than inverting a matrix, which is a very expensive process. Now what we do here is, first of all, we have to realize that boundary conditions have already been applied to the system, because because without boundary conditions applied, it's a useless task trying to find the values of u1 to u4, and in reality u1 to un, whatever the system size is. So they have been applied. So this system, although it's a square system, square K matrix, symmetric, banded, but now it's not singular, so it can be inverted. So now our goal is to convert this system into a system where you have the K matrix converted to an upper triangular matrix. That is, all the elements below the principal diagonal, they are all 0. And we achieve this by operating on the rows, by some row operations. But because we operate on the rows, whatever row we operate on, we must also operate on the force vector term. So this right hand vector, some of these values will also get changed because of these operations. Now once we achieve this, then this step 1 is completed. Step 1 is basically, this is what we meant by forward elimination. That is, you reach a stage where you have the K matrix converted to an upper triangular matrix. Now the second step 2, backward substitution, that is nothing but there's just one number here. This number multiplied with u4, and this number is also known. So you get u4, you can calculate u4. Then you go upwards. There are two numbers, one multiplies with u3, the other multiplies with u4. This u3 plus this u4 is equal to this one. Again, this is known, u4 is known, u3 can be calculated, and so on. You go up and up, and finally you can calculate the first degree of freedom. So you start from the last displacement, last degree of freedom, and you end up with calculating the first degree of freedom, and hence the name backward substitution, because you start from the end and then go backwards. Now if we are going to focus on this one, but there's an identical process. You can do the backward elimination first. In that case, this matrix will be converted not to a UTM but a lower triangular matrix, LTM. And if that is the case, then these elements, these will be all filled and zeros will be here. So in that case, you'll calculate, in step 2 you'll calculate the u1 first, and then u2 and u3 and u4. So in that case, you go and substitute in the forward direction, but you'll get, obviously you'll get the same answers. So let's start this process with step 1. Now I'm going to, for the sake of space, if nothing else, I'm going to demonstrate it on this matrix here. Now the goal is to eliminate these -4 1, this is already 0, so our job is partially done. -4 1 these, they must be converted to zeros. So first take this first column below this one. Now for this, the pivot, the so-called pivot, is 5. This is what you use directly above the column that you want to convert to 0. Directly the number above, that is the pivot, and you have to use this number to convert all these to 0. You can very easily see that if you multiply row 2, this is row 2 with 5, and then we add 4 multiplied by row 1, so here you'll add 0. Similarly in this case here, if you multiply 5 with R3 and then subtract R1 from here, and why this R1 keeps coming up, because this is the pivot. We are going to use this number. Obviously we are not applying this on this column only, you have to apply across the board, but this is how you decide. As far as this is concerned, and this one will become 0 if we do this, and this is already 0, so we don't need to do anything here. So as a result of this first sub-step in step 1, our matrix becomes, the first row is unchanged because there is nothing there to be converted to 0, so you don't worry about the first row. But the second row, now this becomes, this operation, this becomes 0. But now then you have to apply this across the board, including the fourth term. So this turns out to be 0. Please check these calculations, because it's important to see that we are not making any errors here. Minus 14, minus 16, 5 here. Now this, and across the board, so this force factor also becomes 5. Now here you have again 0. This was the point converting to 0, but the other ones, they are the byproducts. You have to be consistent. Minus 20, and here you have 5, and finally this already 0, so here no operation, so this also comes as it is. But if there was a non-zero number here, we would have done some operation and changed this also. Now this has been done. Now similarly, just like we had this column, part of the column, and this was the pivot. Now the next is, this needs to go, this needs to become 0, so the pivot will be 14 now. Same thinking. So in this case we are going to use 14 here. So 14 R3 plus 16 R2. In this, if this multiplies by 14 and then we add 16 multiplied by this will become 0. Similarly, what will make this 0? 14 R4 minus R2. This also becomes 0. But we have to apply this across the board. So the next sub-step, in this case, 5 minus 4, 1, 0, 0, U1, U2, U3, U4. The first two lines, the first two rows, they come unchanged. Nothing here, because we don't need any more zeros on this. The first 0 we require is this one, so, and this was calculated so that this becomes 0, but then you have to apply it across the board, so this becomes this, and the fourth term is also included, and the last, this makes this 0, but then the other also become 0. Also change. Now this, what remains is only this one. This is the last thing. By the same thinking process, one above, this is our pivot now. Now just write pivot here. This one is now pivot. So using this, we'll change this to 0. And what will that be? That will be 150 R4 plus 40 R3. This will make this 0. And obviously some of the other values will also change as a result. So what we get is, if we apply this, the first 3 lines, they appear without any change, because in this case, so our job in every step is becoming smaller and smaller. So the first 3 lines come unchanged. Unchanged, I mean, just going to repeat these, nothing else. 5 minus 4, 1. Our job as far as these lines are concerned has already been done, so we need not worry about these. Third line also, no problem. As far as the fourth line is concerned, yes, these two were already 0. This we made 0 because of this latest use of the pivot, and these also change, and it turns out that the values are this first 3 came as they were in the last step, and this last one, this only changes. Now step 1 is complete. Why? Because we have succeeded in converting our K matrix into an upper triangular matrix. All these are 0. This is end of step 1. Step 2 starts now. It is a simple process of calculating the values of u4, then u3, then u2, then u1, and this is the only way it can be done. You cannot start from here in this approach. 1750 u4 is equal to 5250, which means that u4 is equal to 5250 over 1750, that is u4 is equal to 3. Now the next, you go upwards. The next equation is obviously 0 multiplied by u1 plus 0 multiplied by u2. We need not worry about that. 150 u3 minus 200 u4 is equal to 150, which implies that u3 is what we need to find out. 150 plus 200 into u4 now we know. The last step we calculated this, divided by 150, and u3 is 5. Now we go one step further upwards. Now you have 3 products, 14 into u2 minus 16 into u3 plus 5 into u4 is equal to 5, which implies now u2 is what we need to calculate. 5 plus 16 into u3, and u3 we just calculated was 5, plus 5 into u4 we also know, divided by 14, which is 5. Again 5, these two are 5. Now the first degree of freedom, but calculated at the very end. So you have 5u1 minus 4u2 plus u3, and this is 0, so we need not bother about that, is equal to 0, which implies that u1 is equal to 0 plus 4 into u2 is 5, minus u3 is 5 over 5, that is, turns out to be 3. So in summary, you have u1, u2, u3, u4, 3, 5, 5, 3. So although we demonstrated this algorithm on a very small scale, 4 into 4, but essentially you do the same thing whether it's 10,000 to 10,000 or 100,000 to 100,000, nothing changes, except of course if you are storing your stiffness values in the form of, because it's a banded matrix, symmetric, if you make use of these, then you'll store not like this but like this, so the diagonals become columns here. So some sort of bookkeeping is required before you can apply this sort of algorithm. So pretty much the same approach is used, except some sort of accounting is done so that you keep track of which element actually belongs where. Thank you very much.